Right, there we go. So folks, welcome back from our workshop. Our next speaker is Jay, Hattrick-Simpers. He's from the University of Toronto. He is one of my partners in crime in terms of a co-lead of reproducibility at the Data Sciences Institute. He is going to talk about towards trust and reproducibility in materials AI. And just on a personal note, it's just been wonderful getting to work with Jay these past few months. Just a guy that knows a lot about everything and isn't, he's very generous with sharing that. So thanks very much, Jay. I'm looking forward to your presentation.
Awesome. Thanks for giving me the opportunity to air my particular community's dirty laundry in front of a bunch of strangers. It's gonna be fun. So what I wanted to sort of talk about, right, is more towards this idea that it seemed like a lot of the talks yesterday, I felt like people had identified paths forward and were really, particularly Ben's talk, I walked away thinking to myself, wow, this is a solved problem. For my own community, we are definitely in the sort of aspirational space. And so I wanted to sort of talk to you about why, how this is, but also provide a couple of positive examples of like how you can have really major impact by being open. So it's not working. Oh, so interesting. Oh, it's because I'm not clicked here. Okay, perfect. So if you could find the right material for any number of applications, you could very literally change the world. Right? As a material scientist, I'm constantly on the lookout for new materials, things that could, I don't know, turn CO2 into something useful, capture CO2 from the air, split water to make hydrogen so we can have hydrogen cars, make more efficient turbines. With the right material in hand, you could change the world. And with that type of great response, with that great power, comes a whole lot of skullduggery. And so let me start out by saying 20 years ago, 30 years ago, people in computational material science identified reproducibility as being key, right? It got from the time where we could follow someone's derivation on the side of, in the margin of our letters, to when you're talking about modern density functional theory, molecular dynamics, and now neural networks, random forest, Gaussian process, you can't reproduce somebody's work on your own without access to their data or their models. And so to Ben's point earlier, I'm not sure if he's actually familiar with this, but he's not the only person to say that if you can't get the data in the model, it's an advertisement of scholarship, not actually a scholarship, right? So this is a problem that for my field has been known at least for 30 years, and we haven't done better. And a lot of this comes down to this sort of concept of my problems are different. You'll hear this often when people talk about AI techniques and something was successful and, oh, but my problem's different. Even as recently as like a couple of months ago, I was at a big data for material science conference, and someone asked, this was an honest question, what if someone deliberately adds bad data to our data set? Deliberately to screw up our models. And you're just like, this is crazy. Why would anyone do this? Because in my field, misinformation doesn't kill. Right? If I screw you up and send you down a rabbit hole, and I've already identified that that's a dead end, that's time that you're wasting while I'm making progress. And there are potentially billions of dollars and Nobel Prizes waiting for the people who discover new materials that, again, turn CO2 into something useful, can split water. Sort of tangentially, weirdly, I've heard companies actually say that they'd rather share their models than their data, right? Which I don't know. So it's money, right? And there's this idea within the community that if you closely guard your data, you have an opportunity for massive personal glory. I understand most of you all aren't physical scientists. There's a thing called a superconductor. And it's a material that conducts electricity without any loss. And if you could discover one that happened to occur at room temperature and ambient pressure, the world as we know it would change immediately. Data centers would no longer need all of this cooling, right? Your GPUs would no longer need fans. Energy requirements across the board would drop 40, 50%. The first superconductor was discovered in 1911, Height owns, right? And for a long time, those superconductors that were discovered were only superconducting below 10 Kelvin. What that means is you'd have to be out in space in order for it to be useful, or you need liquid helium as you do with your MRIs. So for the better part of 70 years, people tried like the devil to try to push that temperature up. There's a group at IBM said, let's not look at metals anymore. Let's look at insulators, things that don't conduct electricity, because those will be great superconductors. And they immediately showed a jump from like 10 Kelvin to 15 Kelvin just by switching to oxides. And so there's this huge arms race. And a group in Alabama and Houston discovered a new superconductor that, wow, 93 Kelvin. Liquid nitrogen is 77 Kelvin, and liquid nitrogen is almost free. It's cheaper than beer. So something that's superconducting at 93 Kelvin is game changing. When they went through the peer review process, the allegorical story is they were concerned about skullduggery. So they sent it out to the journal. The journal's editor sent it out to reviewers, selected competitors. And those people tried to reproduce their work and basically scoop them for like half a year until finally they couldn't do it. Paper was accepted and the authors were like, oh, I am so sorry. This is 1985. My typewriter has sticky keys. I wrote it was ytterbium, barium copper oxide. That B stuck, I meant it was yttrium, barium, copper oxide. And so this is entrenched in my community, particularly in the experimentalist, and if you go into industry, it can be even worse. But even still, within my own community, there's many examples of where you can be open with data selectively, firewalling stuff until it's ready for publication. And so this is an example of materials project. It's for my community, massive open computational database. Computer property is about 200,000 odd materials. I consider it one-stop shopping. Whenever I consider a new material system, I go there, see if they've done anything, see what the structure is, see what the lattice parameter is. This is completely open. It has API access. If you're interested in materials data right now, you could go and download every data point that they have publicly available. And it spans phase diagrams, Fourier diagrams, electronic structures. It's a very comprehensive data set. They have 120,000 users, right? And there was a conversation yesterday, like, what's in it for me? And we hear this a lot in our own community. What's in it for me for making my data available to people? They built a community around this. The two major publications for this in less than 10 years have garnered more than 6,000 citations. Personally, I think it's critically still undercited. And the impact, right, both to the PI, Kristen Person is a rock star in my field, and is funded as such. The impact overall to the entire community, including those of us who are doing AI, is just massive. And so here is a clear example where you make your data available to folks, and if they find it useful, it'll come back to benefit you and the community. Code's another matter. So this is another example from tangentially my field, condensed matter physics, where there were two researchers, one at Berkeley and one in Princeton, and they fought for 7 years about the structure of water at -46, like screaming at one another at conferences, yelled at one another. We don't need to go into the details. Again, it's a physical chemistry thing, but basically for 7 years, they wouldn't share code with one another until finally the Princeton group was like, look, here's our code publicly available. You all take a look at it. And after several years of pressure, the Berkeley group made their code freely available. And there was maybe a physics violating bug in it. The idea, of course, is all models are wrong, but some are useful. And so while both models were wrong, the one from Princeton tended to be useful and people kind of agreed with it. Whereas the one from Berkeley, people were a little bit more skeptical about. And interestingly, this whole battle was done over scripts for a program called LAMP, which is probably the biggest, greatest example from my field of why open sourcing code comes back to you 10,000 times over. This is a labor of love by a Sandia National Lab scientist, Steve Plimpton. It's an open molecular dynamics simulation platform. Let's not worry about what that means. It was first published in '95, but it was actually funded by companies and the Department of Energy, who then decided this is so useful, such a great lift to the community, let's make it available to everybody. If there aren't 10,000 users worldwide in a relatively small subfield, I'll smile and eat my hat. If you go to their website, right, there's hundreds of updates, and they're not all being done by Steve. They're being done by other users in the community, adding potentials, finding bugs, and fixing them. It's a huge lift to the community effort, where the original paper has been cited 35,000 times. And literally, it created a whole field from an entire field from whole cloth. So the principle of like, what do I get out of making my code available to other people? What's the benefit to myself? It's potentially massive. It potentially is huge. Just quickly, my own group, we're the Autonomous Discovery of Alloys, right? Autodial. Focus is on building robots, helping them to help us to trust AI, and then making open science platforms to promote equity in the sciences. And so the question of why are we even interested in AI for materials really comes down to, you know, if we consider ourselves cooks, these are my ingredients, right? It's the periodic table. There's about 30 useful elements, right? I can mix them together in different proportions, just the same as you would if you were cooking. But even having the ingredients right isn't necessarily going to get you the appropriate risotto, right? And so processing is super important for us as well. And so when we think about how do we generate reproducibility, we first start with like the building blocks, which are our elements and how we process them. And describing those are hard, but it gets even harder when you start to think about what is a material and what are the length scales and the ways that you have to describe the material in order to arrive at something like, I don't know, carbon fiber for a 787. Properties that start with single atoms promulgate up length scales, acquiring new problems along with them, grain boundaries, cracks, inclusion, all the way up from nano to micrometer level detail to macro, like an engine, and finally into a final product. How to properly featureize a material, even to be able to create a mildly predictive model across these multiple length scales is a non-trivial task, and one that, frankly, we're still working on, right? One example from recent work of mine with NIST, UMD, SLAC, and NREL was super focused, right? Really small problem. Transparent conducting oxides made by 2 different labs. But it took us the better part of a year to really figure out how to properly capture the information, both data and metadata, necessary inside of our experiments in order to permit data exchange and even comparison of results across samples, right? And so you often hear about making data findable, accessible, and interoperable. And the findable part, relatively easy. Make a website. You make a website, you make it free to folks, it's findable and it's accessible. But the interoperability aspect of it involves coming together as a community and sort of forming consensuses around what are the important features necessary to be able to hand a data set off and actually have someone be able to reproduce the work that you've done, or to be able to make the same material or the same model. And this is an example where we all agreed, right? We were working together, and still experimentally our data, orange versus blue, agree in principle and trend, but don't agree in value. And so you start to ask yourself, how do I even begin to, let's set reproducibility to the side. Let's talk about trust. How do I trust a model that comes out of a data set that has this sort of heteroscedasticity to it, right? How do I come to even begin to trust that? And then as a community, and maybe this is the same for the rest of y'all, we don't agree on ground truth, right? If I pick a rock up off of the ground, I believe in causality, right? There's a state of matter. There's something that determines its interactions with the world around it. I can take a measurement of it. I can take an electron diffraction pattern. But I know that the moment I start to interpret the data, I'm living until the ground truth world, right? I'm assuming some rules for interaction. I'm assuming an idealization of state, rules for arrangement. And when it comes to finally training my AI, who I was when I was doing this type of characterization and classification impacts the ground truth that the AI is going to eventually see. And so, you know, ground truth is unknowable, but our approximation is as a crystalline material. But even then, am I a 2-time Nobel Prize winner, or am I a 1-time Nobel Prize winner? Depending on who I am, it's either a quasi crystal or a bad sample that I need to remake. And so this is prevalent throughout my community, maybe yours as well. I'm not entirely sure. But if I give sets of data to experts who all agree that, you know, there are 3 phases that could be potentially present in this material, and just ask them to label the data, even if they'll never agree. And so we think more and more about how do we capture the consensus across multiple experiments, across multiple experts, and then use those types of uncertainties, right? Measure a Shannon entropy on your sample to then evaluate even the efficacy of a model in terms of being able to make a prediction, in this case, a classification. Rohan, I know that I have about 5 minutes left, so I'm going to speed up a little bit. But for us as a community, one of the issues with trust that's been emerging recently is even the reproducibility of AI models on agreed upon data that's been featurized in a community-wide agreed upon method And just switching from something like Weka to sklearn, for the types of data sets that we have, we can see statistically significant variation in the predicted, for instance, holdout MAE or MAPE for data we agree on and for features we agree on. And we're all using random forest. We set the hyperparameters the same. And you switch from Weka to sklearn and you get a completely different model. And it's not just an issue for me. This is a great paper from one of my friends, Logan Ward, who's a staff scientist at Argonne. He was probably at the forefront in my community of, let's make the data available, let's make the model available, let's make the framework for developing the model available. Open source, open code, open data. He generated this wonderful method of comparison. He predicted some new and interesting materials using this framework. Then the original stuff was all written in Java. The whole community moved to Python and Jupyter notebooks. And although statistically, right, the models were able to, you know, come within reasonable similarity of one another, the types of materials being predicted to be interesting for this application, the actual thing that we care about, right? We care about discovering new materials. The best materials aren't even on the list in the new version. And so for my community, this creates an issue of trust. Whereas before I would say, mercury chloride seems like a pretty interesting system. I might dive down onto that. Mercury is nowhere. There's only one chloride on this side. And so this is a problem that my community is just now really beginning to sort of grasp. And so I'm out of time. I'll leave my conclusion slide up. I don't know if we'll be taking questions, but thank you all for your attention.
Thanks, Jay. That's amazing. Does anyone have any questions? If you just raise your hand and then I can call on you.
Yeah, I sort of imagine this is pretty far afield for most of y'all.
It feels like you need a culture shift though, right? It seems like everything, like it's really obvious that there's benefits and yet nobody's really doing it, right? And so it's like, well, why aren't they doing it? There's this culture maybe.
So sort of simultaneously with this meeting, the materials part of the Research Data Alliance is meeting, right? And so the conversation yesterday, it's the same. As a community, we approach this with extreme trepidation, right? Extreme. Everybody's waiting for the journals or the funding agencies to mandate it. Tell me I have to do it. But in the meantime, I'm sure that many of you are associate editors or editors-in-chief and maybe have been on the other side of the program management part. They're waiting for the community to tell them this is the way it has to be done. Otherwise, they're going to continue doing it the same old way. There's movement in the community. There's a sub-community sort of building up around it. And I think that the computational folks are well ahead of people like myself who are more experimental in nature. But it's a challenge. And I think what we should start doing is publicly shaming people by throwing their papers onto paperswithoutcode.com.
I think in economics, a speaker who's coming up later, Lars, he's essentially just mandated this for the main journals in economics, or like for some of the main journals, and that's just been a game changer. It sounds like that's kind of what you're waiting for, maybe.
I think that if we are waiting for it, it'll never happen. We have to make it happen, sort of as a community. And I mean, we have so much lack of trust. in the community in terms of even the data and starting to build, forget reproducing someone's models. Positive bias comes in two different forms, right? One of them is I only publish things that worked and gave me really great values. The other version of it, and maybe this is not as common in other fields, is I did the experiment 100 times. This is the best value I saw. Right? If you think about that value sitting under some sort of distribution, right? Oftentimes it's way out in the outlier space. And so and then we're not often sure what's important to capture in our material. We have a long way to go, is all I can say.
Does anyone else have any other questions or comments for Jay? Oh,
Can I just make a comment? Sorry. I don't really have a question. Thanks for your talk. It was super, super interesting. Just coming from the social sciences and thinking about issues of reproducibility from the physical sciences point of view, it's really interesting to hear like similarities and differences. And I just wanted to make a comment about like thinking about uncertainty, because I feel like in the social sciences, you know, it's so much harder to agree or believe someone's analysis, because the data that we're trying to analyze observational data, you know, who knows what the impact of this policy is, because it's not randomized and it's like really hard to measure. And so I think like thinking about a study and whether we agree on it is like, you know, people disagree and some people agree, and that's kind of fine, and that's part of like what we do. Whereas like you is like what you were sort of describing is like really, really strong, because I guess it's a more physical sort of measurement process. It's like really strong arguments about whether something's right or wrong. And so the tolerance for uncertainty is so much smaller in a way. So that's not a question, it was just sort of a comment, and it's really interesting to hear the differences across the two sort of different fields.
Yeah, we're learning to be tolerant of uncertainty slowly, but I mean, eventually the time comes where you want to make an airplane frame out of it, right? And so the tolerance for the elastic modulus or the yield strength of your material has to be super tight and mega conservative. Otherwise, it's lawn dart territory.
Roy, did you have a question?
Yeah, thanks very much for a nice talk. I just want to make I have a question for you and a comment. I'll just make the comment first. I'm in computer science, and the problem that I see in computer science is that reproducibility means give me the code, give me the data. I will run the data through the code. I will hit return again and again, and I should get the same results. Given that, that's reproducibility. So why should I bother with this? That's the general attitude. Maybe not everybody has this attitude, but many people do. So that's just my comment. But you seem to be a real enthusiast of reproducibility. I share that enthusiasm, but I wonder what it is that convinced you personally that reproducibility was a good idea. I'm hoping to maybe get some insight from you that I can share with my colleagues to persuade them that it's a good idea.
So there have been a number of instances in the physical sciences where people have produced results. Good example is like, I think it's like, I forget if it's the late 1980s, early 1990s, cold fusion. There was also that gentleman from Bell Labs who was making superconducting polymers at room temperature. It basically burned an entire community and multiple people's careers. People saw that, got excited about it, dropped everything they were doing, and dumped everything they had into making room conducting superconductors. And it took the better part of 5, 6, 7 years in multiple Science and Nature papers until people realized that person was fabricating their data. Right? As scientists, the only way we move forward is not to constantly have to fact check one another, but to actually be able to have some confidence that someone has done a good faith effort in terms of reproducing your results. They can be reproduced. I would say that in the computer science, my pull on the way that you're describing reproducibility in computer science is still not that it's factually correct, just that I can get the same numbers as you. And so to me,
that's what I would call computational reproducibility, which is okay as far as it goes, but it doesn't really reproduce the entire experiment, which many people seem unable to digest.
I agree. So to me, it's a matter of, as a community, making sure that we're putting time and resources into projects and ideas that actually have legs. I mean, unless they're reproduced, I don't see why you do it.